So today I'm going to start by finishing showing the examples that I promised yesterday. So you would see more of the decomposition matrices and what you could expect from their shape. So let me just start with where I stopped yesterday. So the example of SL2 of Q. So there were two restrictions. Q was odd and L was odd as well. And you could see that if you're just interested in a decomposition matrix of unipotent blocks, so which means blocks which will contain unipotent characters, you will always have only two simple modules, so two columns here in characteristic L. And there are two cases that you have to look at if you really want the prime number to divide the order of your group. So maybe I should recall it here. The order is Q minus 1, Q plus 1. So there are two cases that you have to look at. Either L divides Q minus 1 or Q plus 1. So because L is odd, it cannot divide both. Okay, and in the first case, everything is somehow algebraic. You have these characters and this induced representation from the torus that you can compute algebraically. You have this decomposition matrix, and on the second case, when L divides Q plus 1, you have in your block characters which are constructed via this cohomology of the linguistic varieties. So these are really the linguistic characters that you have to compute, which you cannot do usually in some algebraic way, whereas for this one you can. Okay, so it's hard from this, based on these two examples, I cannot, you can observe a few things, but it would be hard to conjecture a general behavior of these matrices. So you can see the way that I wrote them. You can see that, and it's implied by the theorem that I stated by Geck and Hiss, that you only have to care about the unipotent characters and their decomposition. Everything else can be deduced from this, from the behavior of these two unipotent characters. Okay, so you have to care only about this square matrix here, and you can see also that they are both unitriangular, but it's a 2 by 2 matrix, so it could be a coincidence. So I have to show you different matrices to convince you that it should be a general property of this matrix. Okay, so we start by SP4 of Q, so a group of type C2. So you can compute its order. It's just a product of polynomials like this, q to the d minus 1, where the d's are the degrees. So here 2 and 4 for this dihedral group. It's more convenient to express this as a product of irreducible polynomials, so cyclotomic polynomials here, q minus 1, q plus 1, and q squared plus 1. So what are the unipotent characters of this group? So they are labeled here by bipartition. So there are two kinds of characters, even in the unipotents. You have the ones which are in the principal series that really you can induce from the torus, which are labeled by this pair of partition, 2 empty, 1 2 empty, empty 2, 1 1. This is the character of the reflection representation for the Weil group, and the last one, empty 1 square. So you have 5 characters like this in the principal series. They all come from induction from the split torus. And you have another one that you cannot construct using this Harry-Chandra or parabolic induction, which is then called Q-spidal, and I will denote it by B2. Okay, so I've arranged them. So this is their degree, the dimension of the corresponding representation. So you can see that the first one is the trivial, and the last one is the Steinberg. And in between, you have dimensions which are polynomials in Q. This is something that was explained by Meinolf. And you can see these several invariants coming here. So this integer that you have to divide by in front of the degree. So you have a half here. You have the maximal power of Q that you can factor on this polynomial. So it's Q to the 0 for the trivial, then it's Q for the 4 other characters, and then Q to the 4 for the last one, for the Steinberg. So this is an important invariant, and I've arranged the characters by decreasing value of this, increasing value of this invariant. Okay, so you can, another remark maybe, something that comes from the theory is that even though defining q-speedal characters, it's based on saying that using this parabolic induction, Harish-Chandra induction, this is something you can read off from the character, from the dimension. You see, the q-speedal one is the only one having some power of q minus 1. Okay, and q minus 1 square is exactly the divisor of the order of the group. So this is something general, something you have to remember for groups of Lie type, is that you shouldn't, when you look at modular representation theory at a prime number, if the prime is large enough, you shouldn't care about the prime itself, but more about the cyclotomic factor that your prime divides. So you have 3 cyclotomic factors here, q minus 1, q plus 1, q squared plus 1. Okay, and a character which is of, not of L defect, but you can say of q minus 1 defect or q plus 1 defect, and so on. So a character which is of q minus 1 defect 0 will be a q-speedal character. That's something that has been proven. It relies on the theory of this Harish-Chandra induction. I'm not going to explain it, but at least all these things, they can be read off from the numerical data that we have. Okay, so like I said, there will be not infinitely many primes to consider somehow, but just each cyclotomic factor at a time. So q minus 1, q plus 1, and q squared plus 1. Okay, so what happens for the first one? So if I assume that L divides q minus 1, I get the identity matrix. Okay, so that's nice. That's also something that I got here. But that doesn't mean that the representation theory is boring here, because remember, what I've written here is part of the decomposition matrix of the block. If I really wanted to write the complete matrix, I will have to write down the non-unipotent part, so all the non-unipotent characters, and these will not, in general, remain simple modulo L. So here you can see that this part, there are still some things happening here, although this is the identity matrix. Okay, but it still tells you something about the property that you should, I mean, it's a theorem that was proved by Puch, is that in this case, and that's the only case for which this really happens, when L divides q minus 1, the conjecture, the derived equivalence predicted by Brouet will be actually a Morita equivalence here. So you get an easy decomposition matrix. It's because of this phenomenon. When L divides q plus 1, it becomes more complicated. You can see there are many entries which are non-zero now. And for L dividing q squared plus 1, you just get 1s in the entries because it's a cyclic defect. So that's a general phenomenon as well. It's not very difficult to compute this one. Okay, so what can you observe from these matrices? Say observations, conjecture. So the first thing, which is really important, is that if you look at the entries, so either in SL2 here or in SP4, so let me show you the entries here, there are integers which do not depend on Q. So something quite striking already, working with a group over a field, finite field FQ. And these decomposition matrices, so the representation theory seems not to depend really strongly on Q, so it's being something quite generic. So that's for the unipotent blocks. You could conjecture or observe that the decomposition numbers are independent from Q. From Q, so not completely, I mean just from, they actually depend only on this cyclotomic factor, so they depend only on the order of Q modulo L. So in this residue field. Okay, that's exactly saying which cyclotomic factor you divide, it's just saying, okay, what would be the order of Q modulo L in FL. That's the first observation. The second one, as you can see, is that the matrices, they all have unitriangular shape, okay, like they did for SL2. So it seems that the basic set of unipotent characters has unitriangular shape. And it's even better. You can see there are lots of zeros on the matrix. And if you regroup the characters like this, so of course for the identity matrix it doesn't make so much sense, but for this one, if you group the characters together like this, you can see that on the diagonal you really have identity blocks, okay? And what do I mean by grouping the characters like this? You can see that there are invariants for these characters, all the numerical invariants that I mentioned before on the degree of the character, so the power of q, the maximal power of q that divides the degree. You see that it's constant on each subset of characters. Okay, so that's something general. You actually have a finer partition, which is the partition into families that comes from the theory of Kashdan and Lustig, and its relation between the linguistic theory and Kashdan-Lustig theory. But you can see that really if you group together by family, there is nothing is really happening between characters of the same family if you restrict to this diagonal block. So unitriangular shape with identity blocks on the diagonal. So as I said yesterday, answering a question that Roman asked, is that one probable explanation for that is that there could be a filtration on your category by families. Okay, so your category of representation, it's not semi-simple in general, but it could be that if you look at the filtration and you look at the associate graduates of that filtration, then you obtain something which is semi-simple. So on each subquotient, it's actually probably semi-simple. That will explain why you get these identity blocks. Okay, so for the last one, that's the same grouping of characters. Okay, there is one last thing you can observe. There is one line which remains almost the same, one row. Okay, if you look at the one corresponding to B2, the cuspidal character, you can see that it's always the same. Okay, so let me highlight it, this one, this cuspidal. So what does that mean here? Well, in this case, it's true for every character. If you start with the character B2 in characteristic 0, and you reduce it modulo L, you get something which is still irreducible. Okay, so you can see that it works in any characteristic here, and this one as well. Okay, so that's a third observation, is that the reduction, the L reduction of a cuspidal unipotent character remains irreducible. Okay, and if you want to be maybe convinced by a bigger example, let me show you one case for F4. So it's a matrix that had been computed by Christoph Köhler. I should have said that the previous one had been computed by Okuyama and Waki at the end of the 90s. Yeah, so this one you can see, so I haven't written all the dots, I got too lazy, but you can see that there are many zero entries. You still have this unitriangular shape with these identity blocks on the diagonal. And if you look at the characters, the rows corresponding to the characters which are cuspidal, they're labeled by F4, so there are 3 of them, and they all remain irreducible modulo L. Okay? And I can say that so all these conjectures and observations, they were made by Geck and Heath. And the last one is now a theorem. Okay, so let me go back to the example of SP4.
The first part only for the square matrix or for
These numbers? No, it would be also. I mean, the parametrization of the non-unipotent characters will somehow depend on Q. So it's there is a similar statement, but it's Yeah. And let's probably stick to the square. But I mean, since but you should still get in integers. I mean, if you look at all the integers which appear, they should be bounded independently from Q, okay? Or independent from Q at least when L is not too small.
Who proved the last part?
It's Gunther Mahler and myself recently. So we used. I mean, maybe I'll explain a little bit about how it works. It's related to how you show the unit triangularity of these matrices. Okay, it's something. So somehow this showing the unit triangularity was. I mean, the methods that were used were really. So used for the first time by Meinhof, but they are not powerful enough to show the unit triangularity in all the cases. But if you adapt the methods, this last bit about the L reduction, you can show it using his construction. Okay, so let's go back to that matrix, and I'm going to explain what are the methods that you need to use, which are not, I mean, they're elementary in their application, but they rely on deep theorems sometimes. But at least in all this theory of Dunning and Lustig, and Meinhof explained that, is that you can actually work it out explicitly. There are computer programs which have been created. Everything is implemented. You can actually ask the computer about all these multiplicities, and just by applying recipes, you can compute such a matrix. So it's if you really want examples, concrete computation, that's doable. Okay, so what will be the methods that I want to explain? So there is, because of this Brauer reciprocity, you can see really the decomposition matrix in both ways. Either you reduce from characteristic 0 to characteristic L, or you look at the columns, okay? Which means you have, and that's actually the way I'm going to try to compute it, is to construct, you want to construct projective indecomposable modules. And then what you have to do is to compute their character. Okay, and by character, I mean that the projective module is over O or over the field of characteristic L. You can lift it to K, and then it will decompose. It was indecomposable in characteristic L, but in characteristic 0, it will decompose. And you can look at all the multiplicities. Okay, and since I'm looking at only the part on unipotent characters, I mean, when I say compute their character, it's just the multiplicities of unipotent characters in these projective modules. Okay, that'll make things simpler. Okay, so what methods do we have? So let me talk about the methods and the pros and cons. Okay, so you want to construct projective indecomposable modules, so you want to construct projective modules. One simple way to do it when you work with finite groups is just to induce projective representation from proper subgroups. Okay, so induce projective modules from proper subgroups. Especially if you start with a group which is L prime, okay, a group whose order is not divisible by L, then every representation is projective, so whatever you will induce from that group will be projective. Okay, and one typical group that we're going to use is inducing from unipotent groups. because the uniparton group will be a P group, and P is different from L in this context that I'm working in the proton subgroup. Okay, what else? The benefit of this method is that you get many projective modules. Okay, so for example, if you start with the trivial subgroup, you induce the trivial representation of the trivial subgroup, you get the regular representation. Of course, it contains all the projective modules. But it's another matter to being able to decompose it, okay? And that's somehow the bad situation of this. The problem with this method is that the modules that you get are too big. So multiplicities are too big. They're not independent from Q, for example, and it's hard to decompose. Okay, but if you think about in which framework you're working, you're not working with any finite group, you're working with groups of Lie type. And what you want to do is some recursive arguments in the proper subgroup that you would like to consider, rather, is our Levy subgroups, so reductive subgroups, and then you want to induce from them. And there is a way to do that, to induce, to minimize the multiplicities, is to do this Harishchandra or parabolic induction. So you can, instead of naively inducing the modules, you can do this Harishchandra induction. And again, if you're working in non-defining characteristic, it will send projectives, it will map projective to projective modules, so of projective modules. But now you're looking at projective modules of Levy subgroups. Okay, so what's the advantage of this method? It's really like somehow the opposite of this one. The multiplicities are small. Independent from Q. And it's easy to decompose in the sense that we usually know well the endomorphism algebra of something which is Harishchandra induced. It has the structure of a Hecke algebra. We know the representation of theory of this Hecke algebra. We can do that. We can use that to decompose. So when I say easy, I'm not saying that's that easy, but at least it's been proven that there are methods to do it. And what's the inconvenience of that method is that like in the characteristic zero case, if you want to construct everything via Harishchandra induction, there are characters that you cannot reach, which are the cuspidal ones. In characteristic L, it becomes even worse. There are more cuspidal modules. So there are projective modules you will never reach using this. So not all of the projective indecomposable module, which I will write as PIMS, will be constructed if you really want to induce from a proper Levy. Okay, so this is as far as the algebraic method go. And you can say, okay, that's exactly what happens in characteristic zero. And what is this, the linguistic theory about is exactly because if I just want to induce from this Levy, which are contained in a rational parabolic subgroup, then I don't get all the representation, so I have to use some extra data, which is given by the cohomology of the linguistic varieties, to compute the new representations. But I can do the same here. Remember that there was a way to construct projective modules is to use this, so I will call it linguistic induction, but what I mean really will be the following. Projective modules. What I mean really will be this, what I denoted last time, this RTG, not of the character theta, but of some representation, projective representation of the torus. Okay? So what's good with this method is that you get, so the multiplicities are computable. Again, independent from Q. You get all the projective indecomposable modules. This is a part of the theorem that I stated yesterday, that if you look at all, for various tori, if you look at all of these characters, you get, inside you get all the projective modules, so that's good. But what's the problem is that it's a virtual character. And that's a problem if you want to decompose it and to compute the character of projective and decomposable module. Okay, and if you want to understand why this is really a problem, it's like if you have a sum of two positive numbers, which is bounded, then you know, of course, how to bound each term of the sum. Okay, but if it's a difference of integers, which is bounded, then your two integers, they can vary, they are not necessarily bounded. So this is exactly what happens because of having virtual projective characters. You could, I mean, it looks like you can't really do anything about it to get decomposition numbers. So I have to explain a little bit how you can use them. I'll do that on this example. And the fourth, method also relies on the geometry, is to use not. So when you do this construction, you use the cohomology of the variety, or the cohomology with compact support, is to use a different variation of the cohomology called the intersection cohomology of the variety. And that helps because usually there are vanishing properties of this intersection cohomology, vanishing in odd degrees, for example. So when you take the alternating sum, you get something positive. It's no longer virtual. And here again, the multiplicities are independent from Q. Okay, you get all the PIMs. What else? You also get some kind of unitriangularity. So basically you get everything you want. So what's the catch here? Is that actually we couldn't prove that it's really a non-virtual character. So that's a conjecture that I want to advertise to you. I will state it at the last for the last minute of the talk. That's you can construct something which looks like not being a virtual character, really a proper projective character. We cannot prove it because it's really constructed from some alternating sum, and it's hard to see that it has some positivity property. Okay, but so I won't use it. But I'll state the conjecture at the end of this talk. Okay, and before using the methods, let me do one remark. Is again why is it's nice to have basic sets of characters when you want to do computations. If you have P and P prime are projective modules, I would say unipotent. So lying in the unipotent block, KG modules. So we've seen, it was during the first talk, that you have, when you lift it to characteristic 0 and consider its character, it actually gives you an injective map in the Grothendieck group. So that means that if you want to compare, if you want to show that two modules are isomorphic, you just need to compute their characters. So their characters are equal. Okay, so meaning that's really this E, what I denoted by E of the class of P is the same as E of the class of P prime. Okay, but since you're working on a basic set, with a basic set, you don't have to check that all the characters occurring in this decomposition occur with the same multiplicity as this one. You just have to restrict to the basic sets, and because of the property of the that the basic set spans everything, you will get the other multiplicities for free. Okay, so just check this on a particular basis somehow. So the characters are equal on the lattice of unipotent characters, spanned by unipotent characters. Okay, so that's really in this in this setting. You look at the columns. If you have two columns which really have the same number, you don't have to compute everything which lies below on the non-unipotent part. But if you know that two columns are equal on this small decomposition matrix, then you know that they should be equal all the way to the bottom of the matrix. Okay, so let's start with SP4. So let me write again what the unipotent characters are. Oh, you have them already, probably not necessary. Let me just start off with the first method. Okay, so I said that inducing projective modules naively, so from unipotent subgroup, you will get big modules which are hard to decompose. So what do I mean by that? Here, there is a way using the unipotent classes of the algebraic group to construct still a family of modules which will satisfy this unitriangularity property. So that means that you'll get this triangular shape for your matrix, except that you don't know anything about the stars entries. They will be, if you look at really the projective modules that you construct, all the stars, they're actually polynomials in Q, so really too big to be decomposition numbers. So you get, like, sorry, just say method one, you can construct what are called generalized Gelfand-Graeff representation. And it's called generalized because the usual Gelfand-Graeff representation, what is it? It's some projective which is induced from a unipotent subgroup to G of some linear character, which is regular enough on the simple roots. And this one has actually character the Steinberg plus non-unipotent. That's how, for example, you get the last column here. You have just a 1. So if you look at this column, that means that you have a projective indecomposable module, which is 1 plus maybe some unipotent characters. But if you already constructed some module, which might be quite big, but still it's like 1 time the Steinberg plus something, so you could take inside the unique projective, the unique indecomposable summon, which has the Steinberg as a constituent, and this one will give you the last column, okay? But even though you cannot actually compute what lies below from that part here, it's enough if you just interested in this square. Okay, and this one they are called generalized because you're inducing from different unipotent subgroups, different linear characters, and you will get like this, like for each character. So in that, I mean, for SP4 you can really make it work. In general, it could become quite tricky, but you can make it work so that you get this unitriangular shape. So they all have one unipotent character plus a bunch of others which lie below. Okay, so there is another thing that you can see here. I'm working with the unipotent block when L divides, or the union of unipotent blocks when L divides Q minus 1. And if you look at this character, labeled by 1.1, its dimension involves like the highest power of Q plus 1 that's possible. So it will be of L defect 0. So it will lie in a different block. So that means two things. First, when you reduce it modulo L, it stays simple. It's a simple in its block. But also, that simple is projective So you get just the column with a 1 and the row with a 1. So in all the computation that I'm going to do now, I can somehow remove this character. It doesn't really interact with the others. It's in different block. Okay, and all the others, the 5 remaining unipotent characters, they're all in the principal block, so they could have various multiplicities. Okay, so let me now use the second method. Second method, what was it? So now I'm not inducing projective modules. I'm Harish-Chandra inducing. So I do this parabolic induction from Levy subgroups. So what kind of Levy subgroups do you have in SP4? The first one, like the minimal one, is a split torus. And when you induce the trivial representation of the split torus, you actually get all the characters in the principal series. And the multiplicities are exactly the dimension of the character, the corresponding character in the Weil group. Okay, so if here you have the Weil group is some dihedral group of order 8. You have 4 representation of dimension 1, 4 linear characters, which are labeled by this bipartition. So they will give 4 unipotent characters, which will occur with multiplicity 1 in this induced. Okay, and the last one, which corresponds to the reflection representation of the dihedral group of dimension 2, it comes with some coefficient 2, but like I said, I don't really care about this one. I can cut by the principal block to get rid of it. So what does that mean if I do this? It means I have a projective module. So here it's really projective. I don't have to add any non-unipotent characters. The trivial representation of the torus. So I should maybe write it here. The torus, what is it? It's GL1 cross GL1. So L does not divide the order of the torus here, which means that the trivial character of the torus, it's already projective. So the induction of that projective is projective, and you get something which might not be decomposable, but still that gives you bounds on the decomposition number. If you take the unique, so inside this one, again, if you take the unique indecomposable summand which involves the trivial character here, then it might be exactly this, or it might be something smaller, but at least you know that then the decomposition numbers will be smaller than 1 in that case. Okay, let's do another Levy, GL2 now. So I'll write it here. Okay, so now what I do, I'm inducing the Steinberg. So what, does it give me? So here L divides the order of GL2. If L divides Q plus 1, sorry. But we've seen for SL2 and GL2 is about the same, that there exists a projective representation with character. So that was for SL2 with character the Steinberg plus some non-unipotent characters. Okay, probably you can see it here. Where in that case for SL2, you have 2 projective indecomposable modules. The first one, its character is 1 plus Steinberg. The other one is Steinberg plus the sum of all the RT prime G thetas. Okay, and for GL2, it's about the same. Okay, but the good thing with Harish-Chandra induction is that it preserves the unipotent characters. If you induce something non-unipotent, it stays non-unipotent. If you induce something unipotent, it stays unipotent. So that means that it preserves the basic set. So when you induce, you can actually forget about everything. Like I said, everything is controlled by the multiplicity on the basic set, the projection on that lattice spanned by the unipotent characters, so you can get rid of it. And now you get only 2 characters. And again, this will give you bound on the second column now, like this. And you can do the same for the other Levy, corresponding to the other simple root. You get now a Levy whose shape is SL2 cross GL1. And when you induce the Steinberg, now it's a little bit different. So this is the Steinberg for, so this character, the Steinberg for SP4, but you can see that in the induction, you permute these two characters and you get the third bounds on decomposition numbers for the third column now. Okay, so now you have bounds, so it's almost as if you had the column, because really the difference between 0 and 1 here, it's not such a big deal. But you can actually prove that everything is 1. So I can say a few words about it. For example, if you take the second column, so it's either a sum of two characters, or it's just the character labeled by 1, 2, empty. Okay? So you can proceed by contradiction. If there exists a projective indecomposable module with character which is, so this 1, 2 plus non-unipotent. Since it's projective, so I said that induction preserves the projectivity of characters, but restriction as well. Okay, you can restrict the Harish-Chandra restriction to, now I'm going to restrict it to SL2 of Q times GL1 of Q is also projective. But if you restrict this one, you can show that it's just the trivial representation of this levy. So 1 LF plus non-unipotent. And you can look at the decomposition matrix of SL2, and you see that, I mean, this is not a projective representation. The only projectives that you have are positive combinations of 1 plus Steinberg and Steinberg. So it's not possible to just have the trivial representation without having the Steinberg, which means that the assumption that you made doesn't hold, and so that the column is actually indecomposable. Okay, and you can proceed this way for the three first columns. Okay, so what remains is this just one entry that you have to determine, and because this B2 is cuspidal, there is no way you can deduce it from any Harish-Chandra induction because you will never reach this B2. So you have to do a little bit of the linguistic theory. So let me, I'm going to explain how it works. And again, that's so for the method 3. What you want is, so I'm going to decompose this character here. So I can directly take something inside, characteristic 0, decompose into the basis of characters of PIMs. So you know that it's a virtual projective character, so it's a combination, linear combination with positive or negative coefficients of characters of projective indecomposable modules. Okay, and again, because I'm working with the basic set here, I mean all the characters, so it's actually it's not really a B theta, it's a B1. So theta is 1 here. What happens is all the characters which are here in this block, they're all non-trivial characters except this one. So when you induce them, you get something non-unipotent. So again, because of the basic set, it's enough to decompose not all this big virtual projective character, but just the one corresponding to the trivial representation. Okay, so I'm going to do this. So I have to switch the notation. Remember that this RTG of 1, so the rational classes of tori, they are parameterized by conjugacy classes of W, or twisted conjugacy classes of the Weil group. So here, I will denote them as minor of Did. So R sub W1, 1 for unipotent, and W is now an element of the Weil group. Okay, so the elements, and it's up to conjugacy, so the elements that I have to consider is, well, first the element 1, then I have S, T, and I will look at ST, which is conjugate to TS, and then I have ST, ST, W0. So I have 5 conjugacy classes, 5 characters. Okay, so I'm going to compute each of this, decompose it on the basis of projective indecomposable module. So the first one, so the element W1 corresponds to the split torus. So it's exactly the computation that we did before. So now I cut by the block. Okay, so I don't have this extra character which is in the middle in the decomposition matrix. Everything occurs with multiplicity 1. And this is just the character of the first projective module. This is just the first column. Okay. And it's just a remark, it's a plus, okay? This is not a virtual character here. Now if I look at the second one, it's a virtual character. It's also a virtual projective character, and it's a difference between the first column and twice the second column, okay? And notice that there is something appearing here. It's not already a pattern, but I'm going to explain where it comes from. There is a minus now in this sum. If you do the same with the other simple reflection, then it's as before. You permute. There are 2 characters that you permute, and it's the effect is permuting swapping the second and the third column, and you get this decomposition like this. Okay. The next step is to go to the conjugacy class of the Coxeter element ST, and it decomposes like this. So there is a mistake here. It's actually a plus. So it's not a virtual character, but still, even though it's a positive combination of characters, it could be a negative or positive combination of projective indecomposable modules. So that's something very important. It's not because you have something which is positive on the basis of unipotent characters that will be positive on the basis of projective indecomposable summands. Okay, and if you do it with this indeterminate star, what you will get are these coefficients, and I mean, how can you deduce something about the star? But you can if you know what sign this coefficient is. Okay, and there is the thing is you can determine which sign it is, and this relies on the deep theorem of Bonafé and Rouquier about the cohomology complex of these varieties. So we'll state it like this. So corollary of a result of Bonafé and Rouquier is that if you start with if P is a projective indecomposable module, and you assume that, and you fix and W an element of the Weil group, if you assume that P does not occur in any decomposition, so R1 V for V smaller than W, so if you want just for, that's equivalent for just for elements of smaller length, it's weaker, then so that means if you look at all the deterministic characters for smaller, for things which are smaller than W, so for example for ST, the things which are smaller are T, S, and 1. If you look at all these ones and your projective character does not occur, then you know in which degree of the complex it will occur, in middle degree, and that means that you will know the sign of the multiplicity of that character in R1W. So then if P does occur in this R1W, it occurs with a sign which is equal to -1 to the length of W. Okay, so let me go back to the computation and explain these signs. So here you're starting with 1, which is the smallest Weil group element. Okay, so any projective module will not have occurred in any smaller delinguistic character. So everything which occurs has to occur with sign -1 to the left of 1, which is 0, so to a positive sign. Okay, and there is a plus here. Here for S, you know already that P1 has occurred, so you have no control on P1. But P2, this is the first time it occurs, and it occurs with a sign -1, because it's -1 to the length of S, the length of S being 1. The same for T. Here you have a minus as a sign in the coefficient of P3, just because it hasn't occurred before. Okay, and for ST, if you do this computation, so P1, P2, P3 already occurred, so you have no control on them. P4, this is the first time it occurs, so you know that the sign must be plus, because the length of ST is 2. Okay, so this is plus, so it doesn't give you any information, but for the last coefficient, you know also that it's a plus, because P5 hasn't occurred. So you know that this coefficient 2 minus star is non-negative. So what does that mean? That means that the star cannot be that big. It has to be smaller than 2. And you get like almost the decomposition matrix like this. So there is a last ingredient to use to show that it's exactly 2 when L is bigger than 3. So there's something strange happening here. It's now using non-unipotent characters that you can show this, but it could happen that you have not enough non-unipotent characters, in which case this number that I haven't written, like as being just equal than 2, could actually be 1. So if the 3 valuation of Q plus 1 is 3, the number actually will be 1. In all the other cases, it will be 2. Okay, so there is the genericity, the fact that the coefficient, they do not depend on Q. For that, you have to assume that L is large enough, or at least the L valuation of your cyclotomic polynomial that you divide has to be large enough. Okay, so let me just finish by stating one conjecture, which will give, as I said, that's all the all the properties that I listed before: unitriangularity, independence of Q, and so on, using this intersection cohomology. So the way these characters are constructed, so by definition, they come from the alternating sum of some variety that now I will denote it by x of w. So it's not exactly the variety y that we had before, or that was in minor Stoke. It's some quotient by the finite torus, but at least it depends on w, and not on the conjugacy class, but really on the element w. Okay, so like I said, the bad thing that it's virtual. So you would like something which is projective but non-virtual. So there are different cohomology theory that you can take. You could take the cohomology with compact support, but that wouldn't change the alternating sum, so it's still equal. Okay, but there is something that sits in between, which is self-dual. So here the dual, the usual dual of this cohomology is this one, the variety being smooth. But there is something that sits inside, so we denote by QW now, is to take the intersection cohomology complex, the intersection cohomology. So now it really measures not just the cohomology of the variety x of w, but something which is a little bit bigger, and how the various local system will ramify along the divisors of this variety, and how you can extend the various constant sheaves on various strata. So it encodes the cohomology of the variety plus some, the singular part of the closure of that variety. Okay, and there is a result by Lustig, which says that even though this one is a virtual character, when you decompose it, you have plus or minus 1, so in characteristic 0. you can change slightly this one so that it would be non-virtual. So there exists a duality. I will call DG. It's called Alvis-Curtis duality. Such that if you look at the dual of QW, it's is the character is up to global sign the character of some representation of G. So if you decompose it, it's something unipotent here. So if you decompose it on the basis of unipotent characters, you get either just only positive multiplicities or negative multiplicities. Okay, but you can't have both at the same time. And the conjecture that we stated with Gunther is that there is the same thing happens in characteristic L, and it's just an observation. We did many computations which were, for example, for F4, of course, but up to the unitary group GU10 to have evidence for that conjecture. Is that up to a global sign, up to a sign, dg of QW is the character of a projective module. Okay, so that's and like as I said, it's not because it's a positive combination of characteristic zero character that will be a positive combination of characters of projective modules. So there is really something more that you have to prove in order. I mean, you cannot deduce that conjecture just from Lustig's result. And yes, so that's one. So one difficult part. I mean, one ingredient for proving that conjecture will be that you see you have these three different cohomology, but you have an extra duality that you can apply once you've taken the cohomology of the variety. But there is no sheaf theoretic version of this duality. We would like some sort of sheaf on your variety, such that when you take the cohomology of that sheaf, you really have some vanishing property, like some parity vanishing phenomenon. But such a sheaf cannot exist. So that's we really have no idea on how to prove that conjecture. But I'm convinced that if there were some geometric interpretation of this duality, which would just that would just follow from that interpretation. And I'll stop here. Thanks. Yes, it's a duality that exchange somehow. It's like tensoring with a sign. So it will exchange the dg of 1. The trivial character, for example, would be the Steinberg. So on each, it respects each Harry-Chandra series, and on each Harry-Chandra series, which correspond to representation of some Hecke algebra, it's just or some Weil groups, just tensoring by the sign. Okay, but that's the thing is, it can also it does not send irreducible character to irreducible character. There is still a sign which occur.
In the context of representations of baby groups, there is this conjecture that the duality interchanges alpha and Lennon's parameters. So I wonder if this can be related.
I don't know. There is there are similar. I mean the way you construct these dualities, it's really by doing some successive Harry-Chandra or parabolic restriction, induction, construct some complex, and there are strange phenomena that like the homology of this complex is just in 1 degree, or some triangularity property for this duality. But I mean, I'll be like really interested in whether there is at the level of the Hecke category, for example, if there exists such a duality. There is, I mean, these objects, for the Hecke algebra, they represent the standard basis and its dual. Here, one of the Kazhdan-Lustig basis, but if you want to represent the dual, usually you're stuck. That's the problem we have here.
So how close would you expect this projective module that exists to being a progenitor?
It will be because I mean, not itself, but if you take the sum over all the elements W, it will be a progenerator. So you will have a progenerator which is independent from Q somehow. And then so that would imply properties on, of course, on the endomorphism algebra of that projective, which is your group, or at least the unipotent block. So that's, in terms of characters, this one, they got the same number of characters as this one. So if you know that already all the PIMs occur here, they will occur here.